I'm Kevin Hamilton.
I'm Teresa Soriano.
And I'm Emily Simso.
And this is Iggy.
And
this is the physics of a cartwheel. Yeah!
So this is our person standing on the flat surface before the cartwheel. And we'll say this point is our center of gravity. And then we'll have that point translate into our free body diagram. And we'll list a couple of the forces that are acting on the person. So first we have the weight, which is just the mass of the person times the force of gravity. And then we'll have, obviously, the normal force, which opposes it, which will just be equal to the weight of the person. And then we'll have the force that the person applies to do the cartwheel, which will be later explained in the video. And then opposing that force, we'll have air resistance, which in this case will be negligible because the person is not in a windy condition.
So the radius is going to be the center of gravity to the top of Teresa's head. The kinetic energy has two parts. The first part is linear, and it's 1/2 mass times velocity squared. And the second part is rotational, 1/2 inertia omega squared.
The velocity of the cartwheel is the initial velocity plus the absolute value of the force applied divided by the mass, all times the time it takes to complete the motion. In an ideal situation, over time the velocity would turn constant, meaning there would no longer have to be any force applied to continue the motion. The moment of inertia, or I, is the mass times the radius squared, and the radius is the distance between our center of gravity to the top of your head.
Because I have a greater mass, the force required to complete the cartwheel will be higher. Because my mass is greater and my radius is also bigger, the moment of inertia is greater, thus it opposes my motion.
So in conclusion, it's easier to do a cartwheel if you are smaller because you have less mass and a smaller radius, so you require less force to go around. However, this can be overcome with good technique.